So thank you and hello also from me. I will start with the weather briefing today. My name is Liliane Hofer and I'm working at GeoSphere Austria. And if you now ask GeoSphere Austria, I've never heard that before. It's the weather service formerly known as ZAMG. And in the beginning of this year, the ZAMG was pooled together with the Geological Institute of Austria. And since then we call ourselves GeoSphere Austria. I'm working as a meteorologist, but not at the headquarters in Vienna, but at a regional office in Salzburg. I'm a forecaster, I'm a member of the EUMeTrain project, and I'm also working in the field of environmental meteorology. My favorite satellite images are the ERMAS and the day natural color RGB, and therefore I'm really happy because I can show you some nice features with the help of these two today. But before I start, I would like you to show me where you're sitting at the moment. So I hope you can use the annotation tools now. As I've mentioned before, I'm sitting here in beautiful Salzburg. And the weather today is partly sunny, partly cloudy. It's not too warm. In the evening, there might be some thunderstorms or rain showers coming from the Alps. But at the moment, it's really nice outside. Okay, so I can see you annotating. We have many sitting in Central Europe, some from Eastern European countries. I will give you another 10 seconds for annotating. Okay, we have someone in Spain. Okay, we have also a Scottish participant. Nice to see that. So thank you. I will now stop the annotation tools and continue with this presentation. So I would like to start this weather briefing with the ERMAS RGB from today, 0 UTC. And as you probably all know, the ERMAS RGB's main use is to distinguish between different air masses. You can also use it for analyzing dynamic processes. And it's also very good to distinguish between high clouds or high reaching clouds and mid-level clouds. And this can be clearly seen if you take a look at Central Europe. There you can see some convective cells over Italy and over Croatia. And these appear really bright, really bright white. Also this convective cell over Africa appears bright white in difference to the mid-level clouds over large parts of Northern Europe, which appear more yellowish. What you can also see very, very nicely in this image are the different air masses. So in the northern part of this image, you have more bluish to purplish colors, whereas in the southern parts, you have these greenish orange colors. And this is how it should look like, because the more bluish colors show cold and polar air masses, whereas greenish colors indicate tropical air masses. This is all due to the ozone content of the air mass, and this is due to the ozone channel, this IR 9.7. And if the air mass is ozone rich, then you have nearly no contribution from this green channel and more bluish purplish colors. And if the air mass is ozone poor, like in tropical regions, then you have a large contribution from the green channel. That's the theory behind it. A limitation in this air mass RGB is that you can not really see low clouds, so you have to use other tools for seeing low clouds. And as I've said in the beginning, you can see dynamic processes going on. That's due to descending dry air masses, which are assigned for PV anomalies. They appear in reddish colors because dry air means that there is no contribution from the blue beam. The stratospheric air masses are also rich. That means there is no contribution from the green beam. And these air masses look really reddish. So PV anomalies, which can be assigned for ongoing cyclogenesis, for deformation zones, for jet streams, they appear in this red or purplish colors. And I would like you now to show me where you think that the jet streams are located in this image, or with the help of this image. Where would you think that jet streams are located? You should have the annotation tools now. And okay, I can see some first drawings going on. Yes, this looks all very good. Who is so brave and will try to find the jet streams in the southern part of the image? Okay. Of orange colors in the southern parts of the image. Okay, I will, yes, and show you the solution in the next image where I just overlaid the isotext, and now it works. Here you can see, okay, this was really easy, this one, this elongated jet stream over the northern part of Europe, also here over this low, and in the southern parts we have two branches of jet streams. I have to admit this western jet stream here cannot be seen too good with the help of this RGB, but this one, most of you found it very good. What more can we see? We have here still some more areas with reddish colors and orange colors. And if we now take a look at the 6 UTC image, you can see that this area of reddish colors got bigger. The red color got more pronounced. It's more dark red. And some of you may think, wow, what's going on there? There's huge PV anomaly. But if we now take a look at the dynamics, so if we now overlay the PV 1.5 isoline, then you can see nicely the jet axis. You can see some PV anomalies going on here, but in this big red area, there's no distinct PV advection going on. So what's the reason for this? And this is another limitation of the AMS RGB, that if the ground, the surface is really hot and really dry, then you also get these red signals, these red colors. I have here now, it's still 6 UTC, it's now the dust RGB, just that you have a better contrast to see the synop observations, because in these desert areas, take a look at the temperatures. We have surface temperatures around 34, 37, 33 degrees. And the dew points, which you can see here, the numbers below the surface temperatures, they are really, really low. We have 2 degrees, 3, 5 degrees. So this area is really an area of very hot and very dry air. And this also, these areas, they look also really, really reddish in the AMS RGB. So most of you probably know it, but really keep that in mind, that in the desert areas, the red colors can also mean that the air is very hot and very dry. So let's stay with the dust RGB over here. You can see also surface features with the help of the dust RGB. So if you take a look at all these desert areas over here, they're really hot, and you can see these hot surfaces are or have this light blue, maybe even cyan colors. The main goal of the dust RGB is, as the name implies, to make dust and ash clouds visible. And for this purpose, I now enlarge this area that you can see. Yeah. So you can see also the area of Iran and Pakistan over here, and especially over Pakistan. You can see this pinkish color, which are colors which are typically for dust clouds or also ash clouds. And so that means that there is some dust in the air. As the season, as we have summer season, we are really lucky because we have already some visible images for 6 UTC for this area at hand. So we can take a look at the day natural color RGB, and here where you have seen the pinkish structures in the dust RGB, you can see that it's all a little bit hazy, so there's really some dust in the air. Yeah, that's now the day natural color RGB. As I've said in the beginning, it's another one of my favorite satellite images, of my favorite RGBs, because when you look at the day natural color RGB, you see the Earth as you would see it if you were sitting on a satellite. So the desert areas look brownish, the vegetation areas look greenish, the clouds are whitish. The only big difference is that ice features and ice clouds, they appear in the cyan colors. But it's really nice to look at. You can detect lots of features. And in this particular image, you can see a very special feature. If you take a look at the Red Sea, at the southern part of the Red Sea. Wait a minute, I can zoom in. So now you can see better. You can see here these bright features. You can see a sun glint, yes. And what is a sun glint? It's more or less that the satellite is blinded by the sun. So if the sunlight reflects off water surfaces at the same angle that the satellite sensor views it, then you can see this feature. It can only be seen with the help of visible channels. And you can see also these small lakes, these water bodies over Africa here. Also here you can see these bright features. So it's really a nice feature. You cannot see it with thermal channels. Oh, Jochen says it's also seen in infrared 3.9. That's probably because 3.9 has also some visible component going on. But I think, Jochen, you can tell us more in the end. Oh, yes, okay. Yes, and so I have a question for you. As I've said before, sun glint can mainly be seen with the help of visible channels. So in which of these 3 satellite products can you see the sun glint? Or the question could also be, which satellite product has a contribution from visible channels? So you should be able to use your annotation tools now. Now highlight the images where you think you can detect the sun glint. Okay, I already see some answers, but I think it's no big secret that the answers look very good. Uses 3.9 channel. Okay, I think you've all had the right answers. So let's show it to you. Most of you probably know the satellite products here. We have on the left-hand side the sandwich product. This consists of 2 layers. The bottom layer is the high resolution visible channel, which allows it to see the sun glint. You don't see it as pronounced as in the RGB images, but you can see these bright features over here. You can also see these water bodies over Africa. The sandwich product is also very nice for highlighting convective structures because the cloud tops, the temperatures of the cloud tops are highlighted, as the top layer of the sandwich product is a color enhanced infrared channel. The satellite image in the middle is the dust RGB, and as you can see, there is no visible channel involved. Also, the infrared 3.9 is not involved, and you cannot see the sun glint over here. It doesn't show. And the third image on the right-hand side is the convection RGB. It uses, on the one hand, the difference in reflection between the near-infrared 1.6 and visible 0.6. So that means that the sun glint is, you can see it highlighted in more bluish colors. And it also uses the 3.9 channel. As Jochen said, this also shows a sun glint. So you gave all the right answers. Nobody has chosen the dust RGB. Very good. So, and the last image I will show you today is again the EMS RGB, because it's now the image from 9 UTC, and you can see due to the solar heating, white parts of northern Africa have now these really reddish colors, and that is due to the heating of the surface. And please be always careful during the summertime. If you look at desert areas or at hot areas, that the red features may not indicate PV anomalies in these areas. That's it from my side. You have seen the convection RGB before, and I think you will hear more from it from my colleague Christian Resch, who will show us a nice analysis of some convection going on last week or the week before. Okay, so thank you for your attention.
As already introduced, I'm also from the GeoSphere Austria. I'm also sitting in the regional office in Salzburg. My name is Christian Resch. I was born and raised in Salzburg, then went to study to Innsbruck, which is also in Austria. I'm now working also as a forecasting meteorologist at the regional office in Salzburg. And yeah, the rest is basically around nature and music and sports. So let's jump right in. as Lily said, I will talk about a convective event we had a few days ago. It was really the season opening for severe weather in Central Europe. You can see on the right-hand side, you can see the Estofex forecast or warning chart for severe weather warning for the 22nd of June. And as you can see, they pushed the level 3 warning, which is the highest in their threshold for Central Germany. It's a bit of a spoiler here because you already can see what happened, but I guess you may have heard about the event. And we're going to have a look at that. So we're going to start with a simple recipe kind of thing. So what are the basic ingredients for severe weather or for convective storms to form? First, we need moisture, low-level moisture, which can be lifted then. Then we need some kind of instability, so steep lapse rates, and we need a lifting mechanism on synoptic scale. And now we're going to have a look if this recipe is fulfilled or not. And at first, we're going to take a look at the moisture. You can see here the SYNOP surface observations from 6 UTC on the 22nd of June. And as you can see, we have really high dew points. 18, 18, 17 over France, and also in Germany 16, 17, so pretty high. And also the temperature was not that high. Of course, it's in the morning. And we also have we can also see some showers already in France and in the Benelux states. We're gonna take a look now. No, it's not working. Yeah. So this is the surface chart. And you can see we have this low pressure system, and the surface low located over France. So this is about the lifting mechanism then. So we have a synoptic scale lifting mechanism. This will wander across Germany during the course of the day. So it's going to wander northeastwards. You can already see the frontal system dividing or crossing Germany, and you have this cold front over France. Yes, so lifting was also there, definitely. You can also see this this low pressure system in the air mass RGB, and as Lily already said, the reddish colors in the air mass RGB are indicators for polar air and for cyclogenesis. And now you can see that the whole lifting will take place, in the region of the surface low. Basically, you can see the reddish colors getting sucked into the low pressure system and into the area of our forecast. So the next slide, it's a bit slow. I don't know why. Yeah. Here I put in the barbs, the wind barbs. So again, about the reddish colors and the greenish colors. So what can we see in this air mass RGB? We have a large area of warm air advection. It's indicated by the wind barbs, as I said before. And we can see it in the air mass RGB because we have this these greenish colors. It's again not working. Wait a second. Yeah. And the greenish colors mean warm ozone poor tropical air masses, as Lily said before. And as we all know, warm air advection is always a good fuel for thunderstorms and for instability. So we can see these nice lapse rates here in these observations. These are radio soundings from Bavaria, and as you can see, I mean, it's basically dry adiabatic lapse rate. So it's on the left-hand side from Schöngau, which is in the southern part of Germany, and from Munich. If you take a look at the values, we have a cape of 2,600, so that's not that bad, and a deep layer shear between 0 and 6 kilometers of 43. So this day was it's a pretty impressive sounding, I would say. And it's no wonder that these storms got that heavy. Yeah, so if we now think about it, we have all the ingredients which we need for really severe convection and severe storms. We have lifting, moisture, deep layer shear, high cape values, instability. So we can now have a look at what happened then really. You can now see the convection RGB, but I overlaid the radar from 6 UTC. There's nothing too crazy going on so far. We already have some convective showers over France and also over Germany. But there is already some lightning, but as I said, it's not that crazy. But in the course of the day, the low pressure system will move more eastwards and start to cross Germany. And now with the convection RGB. And now I would like you to show me. So assign, allow to annotate. So you should now annotate, and now you can show me. Yeah, okay, thank you. The areas where convection is happening and where fresh updrafts are happening. Yes, very nice, very nice. I think you all know it. It's a classic. We have then these yellowish areas. We have thick ice clouds with small ice crystals on the top and very cold cloud top. So basically these two circles then will be the main two supercells which produced large hail, severe gusts, and some severe flooding. The reddish areas, however, are more the older clouds with large ice crystals already and not very cold cloud tops. This picture is from 12 UTC, so you can see the storms are moving. And now we can have a look at the cloud top features. This is the sandwich product, which is great for nowcasting. As Lily already said, it's a combination of high resolution and infrared information, so high resolution visible and infrared, which makes these really cool pictures. And now I want you to show me some overshooting tops or a cold view, which are always indicators for nice convection going on, for fresh updrafts, for strong updrafts. So I think now you can annotate, and maybe you can show me some overshooting tops or a cold U if you see one, or a cold ring. Yeah, very nice. Yeah, perfect, perfect. The right picture is from 15 UTC, where the storms are already in central Germany or in the northern part of Germany. The last one, the left one, is from 18 UTC, which is barely the last picture which can be used for sandwich, because it uses the visible and then it gets dark, obviously. And you can also see some part of Austria here, where we also had a really nice thunderstorm going on, which also produced hail with sizes of around 5 centimeters. You can see over Munich a very nice anvil and this very nice cell. They also had a lot of hail in Munich due to that storm. And I will show you in a second the solution. So here I put also the radar on, again from 15 UTC, and you can see, even though the anvils are pretty big and appear massive in the seen from above, it doesn't necessarily mean that the whole area is affected by severe weather or by hail or whatever. But the overshooting tops pretty much overlay with, or the areas you marked pretty much overlay with the radar observations, with the strongest precipitation and the strongest cells. And the take-home message: just because the anvil is big doesn't mean the whole area is affected by severe weather, which is interesting. And then we can have a look at the surface observations. Then I've taken the weather reports from the ESWD, and you can see pretty much the area where we observed the storms, the cells. In green, you can see the observations for large hail. You can, in yellow, see the severe wind gusts. Yeah, in blue, the flash flooding, and there was even one tornado observation. However, I didn't manage to find a verification for that really. And Matthias, I think you're also here from DWD. He told me that there is no verified report yet. So this is not really, we're not 100% sure that this would happen. This had happened. Even though the ingredients were perfect, we had low cloud tops, pretty good shear, a lot of cape, so a lot of shear and cape. It would have matched the pattern. Yes, so this was a short overview about this severe convection event from 2 weeks ago already. And I thank you for your attention.